if the so if the radioisotopes have a long enough half-life to be able to move towards the outer layers of the star before the explosion occurs, the gamma rays that come from the decay of these isotopes can escape the star, and these can be detected via gamma ray observatories that are mounted, say, on satellites or balloon observatories. So titanium-44 has a half-life of about 60 years or so, and it can decay to scandium-44 and then eventually to calcium-44. And nickel-56 decays similarly to cobalt-56 and then eventually to stable iron-56. So in order to properly understand the observed abundances of titanium-44 and nickel-56, nuclear physics can provide a lot of constraints, such as nuclear reaction rates and reaction cross-sections, and so on and so forth. So there have been a lot of sensitivity studies that have been performed throughout the years for the production of titanium-44 and nickel-56. And most of these sensitivity studies are actually performed to identify which nuclear reactions which nuclear reactions can explain the abundances of these two isotopes. So I'm only showing a few of them here, but there are so many more throughout the years. Focusing mainly on two sensitivity studies that came out just 2 years ago in 2020. These are the latest sensitivity studies for CoCoLab supernova. And one of them by Subedi and others have shown, they have done simulations for progenitor stars ranging from masses of 15 to 25 solar masses. And they have, out of all the reactions that they have used for these sensitivity studies, they have, for the nitrogen-13 alpha P reaction, they have used a reaction rate variation of a factor of 100, which actually shows you how uncertain the reaction rate is at this point. And I will say more about the reaction rate uncertainties later in my talk. And this work has shown that the nitrogen-13 alpha P reaction actually affects the abundance of titanium-44 and the ratio between observed titanium-44 and nickel-56 in these progenitor stars that they have used for their models. So when the nitrogen-13 reaction rate is increased by a factor of 100, they have shown that the titanium-44 abundance actually decreases. So another sensitivity study that came out in the same year used a different progenitor star of 12 solar masses. And they have used, for the sensitivity study, the full reaction rate library from StarLib, which includes 3,403 nuclear reactions. And out of all of these reactions, they have identified 48 key reactions that play a role for nuclear synthesis in CoCoLab supernova. So for this measure, for this sensitivity study, they have used reaction rate variations of a factor of 2, a factor of 10, and a factor of 100. And from all of these calculations that they have performed, they have shown that the nitrogen-13 alpha P reaction affects 7 different isotopes that are created in CoCoLab supernova scenarios. Another reason as to why the nitrogen-13 alpha P is important, it has been shown in pre-solar grains, silicon carbide pre-solar grains, that the observed carbon-12 to carbon-13 ratio in these pre-solar grains are actually lower than what is observed in the solar composition. So that means that these silicon carbide grains show a much higher carbon-13 abundance. So a possible reason for this was suggested by Marco Pignatari in 2015, where he suggested that just before the supernova explosion, there could be some ingestion of hydrogen into the helium layer, which can actually react with the carbon-12 present in that layer so that it will create nitrogen-13. And then this nitrogen-13 can in turn beta decay into carbon-13. So this would increase the abundance of carbon-13 in these environments. So, but the nitrogen-13 that's created in this manner is actually affected by the alpha and proton capture on nitrogen-13 in this environment. So it is important to constrain the reaction rate of the nitrogen-13 alpha P reaction and the nitrogen-13 P gamma reaction for these relevant temperature regions. So they have also shown by observing the abundances in these pre-solar grains that the carbon-13, high carbon-13 abundance in these pre-solar grains can also affect the nitrogen-15 abundance as well. So for most of the pre-solar grains coming from supernova, they have shown that they also have a nitrogen-15 abundance from the decay and different reactions on carbon-13. So this is also one of the reasons why it is important to measure the nitrogen-13 alpha P reaction. So the current reaction rate for this nitrogen-13 alpha P reaction comes from the ReactLib database. And previously, there have not been any direct measurements that have been performed. And the only reaction rate in ReactLib that has been calculated has been using the data from the inverse reaction of oxygen-16P alpha. So the data that has been used in order to infer the nitrogen-13 alpha P rate in this ReactLib library comes from several measurements that have been performed in the 1970s using various activation techniques. And two of these measurements I have shown here on the left. So most of this oxygen-16P alpha data has been performed from the late 50s to the late 80s or so. And a full compilation of these data sets were later done in 2003 by Takacs and others. And that is what is shown here on the rightmost plot, where they had compiled all of the different available data sets. And they have done a sort of a fit for all these data sets, so that this fit can be used later on to calculate the reaction rate. But I should mention that right as of now, the ReactLib data rate only uses the data from this 1973 measurement by Nero and others. So I will compare the results from the measurement that I'm talking about today with this fit from Takacs for the previous oxygen-16P alpha data. One other thing that I should note is that there is not that much information available from these 1973 measurements, and the current reaction rate in the ReactLib library has no uncertainties given. So this is one of the major concerns and one of the reasons as to why we wanted to measure this reaction. So like I mentioned before, regarding the uncertainties of this reaction rate, there is not that much information available on the previous oxygen-16P alpha measurements that have been used to calculate the reaction rate. And another issue is the applicability of Hausser-Feshbach models due to the low level density of fluorine-17, that is the compound nucleus of nitrogen-13 plus alpha. So in this mass region, until recently, there was an associated factor of 10 that was used for Hausser-Feshbach calculations. Another very major uncertainty for this reaction rate comes from the fact that for high temperatures that are relevant for core-collapse supernova, excited states of oxygen-16 are expected to contribute to the reaction rate. So if you only use the reaction rate from the inverse reaction of oxygen-16P alpha, it only provides the reaction rate contribution coming from the ground state of oxygen 16. So the alpha P 0 channel to be exact. But if you have much higher temperatures, you can populate much higher, excited states of oxygen 16 that can also play an important role for the reaction rate. So very recently in 2020, there was another experimental measure, experiment that was performed by Meyer and others to try and see if they can constrain this nitrogen-13 alpha P reaction rate. So what they had done is a indirect measurement. They had used a carbon-13 lithium-7T alpha transfer reaction, and they had populated states in oxygen 17 and tried to match them with states of the mirror nucleus of fluorine 17. So what I have shown here on the left is the results from their measurements. So from their experimental measurement, they have been able to match several of their oxygen 17 levels to known levels in fluorine 17. But there are a lot of uncertainty coming into this method, where for most of the relevant levels in fluorine 17, most of the alpha and proton partial widths are not known. So several educated assumptions had to be made for the partial alpha widths in order to obtain a spectroscopic factor. So there's due to all of these uncertainties that's coming in, that they have roughly a uncertainty factor of 2.5 for the reaction rate that's associated with the partial alpha widths in fluorine 17. So in the right here, they have sort of compared the reaction rate that they have observed. They have calculated with the current rate in the reactive library and the StarLib reaction rate library. And as you can see, there's almost as few 1 to 2 orders of magnitude difference in uncertainty in this current reaction rate. So a direct measurement was solely needed in order to constrain the reaction rate. So there are several methods that can be used for doing such measurements. Either you can measure this directly or indirectly, as I just mentioned in the previous slide. So direct measurements are very difficult to carry out due to the low reaction cross sections and the need for high intensity radioactive beams. And the extrapolation techniques that are needed to extrapolate to low astrophysically relevant energies can introduce significant uncertainties. So active target detectors such as MUSIC, TechSat, or ATTPC can be used to measure such direct measurements, and they have been used for such measurements as well. And at the same time, you can do transfer reactions like lithium-7T that I mentioned in the previous slide, using a big range of experimental setups worldwide, of which some I have shown here. So we decided to do the first direct measurement of the nitrogen-13 alpha P at Argonne National Laboratory. So for anyone who is not familiar with the layout, here's basically a layout of the ATLAS facility. And the detector that we used for this measurement was placed in front of this spectrometer that's highlighted in red towards the top left. So the detector that was used for this measurement is called MUSIC for short. It stands for Multi-Sampling Ionization Chamber. This is an active target detector where the detector gas is also the target gas. And one of the main advantages of this detector is that it can be used with very low intensity beams to measure low reaction cross sections. To give a basic overview of the detector itself, a picture of the detector is shown here on the left. It is a very simple detector where you have a segmented anode on the top and a simple cathode on the bottom. And this entire volume is filled with helium gas, for example, for an alpha P measurement. And there is a frisch grid right below this anode pad. And the anode is segmented in order to help with identifying the different reaction channels and the beam, etc., and different contaminants of the beam. And as you can see here, the anode has 18 different strips, and the center 16 strips are segmented into two, in a sort of zigzag pattern. So this detector is very simple, where it only has 36 channels in total, 34 coming from the anode and one each coming from the grid, the frisch grid and the cathode. So one of the biggest advantages of this detector is that it is almost 100% efficient due to the segmented anode structure. And due to this anode structure, it allows you to measure a wide range of center of mass energies just by using one single beam energy. So this is a big advantage of using such a detector. And when you do measurements using this detector or any such detector as this, you want to be able to accurately characterize the beam that's coming into the detector. So you want to be able to count it. So one of the biggest advantages here is that you do not need any sort of auxiliary detectors, because the music detector can count every single particle that's coming in, that's entering the detector volume. So we have used different gases for this music active target detector. We have used helium in the past, different isotopes of neon, argon, and methane, and so on, with a wide range of pressures ranging from 150 to atmospheric pressure, 152 to atmosphere. And recently we have shown that with a pure helium gas, the detector can handle beam rates of up to about 80 kilohertz. And this detector has been used to measure alpha P reactions, alpha N reactions, and very recently P alpha reactions as well, relevant for nuclear astrophysics. Like I mentioned before, this detector has been used for several alpha P reaction measurements. And these measurements are relevant for various scenarios like X-ray bursts and nova nucleosynthesis. And I have listed several measurements that have been performed with this detector, and some of the results have been published, and some of them are under analysis as of now. So to give a little bit of detail about the actual experiment, a carbon 12 primary beam was used to create radioactive nitrogen-13 for this measurement. And the nitrogen-13 was created using a DN reaction. And the beam intensity of the nitrogen-13 was roughly about 300 to 500 particles per second. So as I mentioned, music can handle very low beam intensities and be able to do a really good measurement. And the gas for this detector at this point was a helium-krypton mixture at about 400 torr. And the energy of the nitrogen-13 beam right at the entrance of music after the entrance window was roughly about 35 MeV in energy. So as the beam enters this music gas volume, and while it's traveling through the gas, the energy that is lost in each of the width of the strips of the anode pad can be detected and calculated. So as the beam travels, from what you see on the plot on the right is basically a plot of the energy losses for the different reaction channels and the beam. So the beam, the Bragg peak of the beam was roughly around strip 14 to 15 in the anode pad, which is shown here on the black lines. And the energy loss is proportional to the square of the atomic charge of the particles. So whenever there is a higher Z particle that's created, there'll be a jump in the energy loss, as you can see. And then by detecting exactly where this jump occurs, you can identify the different reaction channels. So what I have shown here on the left is the nitrogen-13 alpha P reaction that's shown in red, where you see the energy has a much higher jump due to the oxygen-16. And the nitrogen-13 alpha-alpha reactions are shown in blue. So using these techniques, once you identify exactly where the reaction occurs, you can sum the energy losses of different strips in order to create a delta E plot that's shown here on the bottom right. And these kind of plots can be used to further separate out the alpha P events from the other reaction channels. As I mentioned, MUSIC can count the full amount of beam that comes into the detector. So for each of the different anodes, anode strips, when you actually, it's very simple to calculate the total reaction cross-section, where you just count the number of events that happened at that particular strip, and then that will give you the total reaction cross-section. So for this specific measurement for the nitrogen-13, we were able to obtain total reaction cross-sections ranging from strip 1 all the way up until strip 9 or so. So that covers a center of mass energy range of about 3 to 6 MeV full range. So the experimental cross sections are shown here in this plot with the black symbols. And the energy uncertainty in this measurement comes from the fact that we don't really know exactly where the reaction happened within the width of one anode strip. So that sort of determines the energy uncertainty. And the cross-section uncertainty, taking into account all the systematic and statistical uncertainties, have been shown to be less than 10% for most of the higher strips. And the uncertainty becomes larger for most of the lower strips, and the uncertainty becomes larger the further down you go in strips. So what I have shown here is a comparison of the experimental cross-sections with the theoretical calculations using tallies for the different, for the population of different channels in oxygen-16. These calculations were performed by Peter Moore using tallies. And as you can see, for the total alpha P reaction cross-section, towards the higher center of mass energies, the alpha P2 channel starts to dominate significantly. So that means that in this case, the nitrogen-13 plus alpha reaction ends up populating the second excited state of oxygen-16. So this is one of the big points of this measurement, where if you only use the oxygen-16 P alpha data in order to calculate the reaction rate, you are only going to be able to use the alpha P0 channel. And for the higher energies, as you can see here, the alpha P2 channel also starts to dominate. So this measurement that we performed at Argonne actually calculates the total alpha P reaction cross sections, which includes the contributions from all of these other excited states of oxygen-16 as well. But towards the higher energies, if we populate states in oxygen-16 that are above the alpha decay threshold, they can decay to carbon-12 plus alpha, and we are not sensitive to such reaction channels from measurement. the results from this current measurement was converted to astrophysical S-factors and compared with other previous measurements. So these results have been submitted as a letter to PRC, and you can find a full detail of this experiment and the results in the archive if you follow this link. So one of the major points in this plot here is that we have measured the astrophysical S-factors for a center of mass region of about 3.2 to 6 MeV. And as you can see, the green curve here is the fit that I showed in the earlier of my talk, where the S-factors were coming from the oxygen 16P alpha data. So the oxygen 16P alpha data, when converted to nitrogen 13 alpha P, only amounts for about 10% of the total reaction rate for energies above 3 MeV or so. So this really affects the high temperature region for the reaction rate in nitrogen 13 alpha P. So in order to get a more concise reaction rate, we combine the data from our present measurement with the low energy data from the previous measurements. So the oxygen 16P alpha data, this green curve extends from about much higher energies all the way up to 1.2 MeV. And there is no oxygen 16P alpha data present for energies below that. So for the lowest energies, we adopted the astrophysical S-factors from the alpha transfer measurement of Ann Meyer and others. So as you can see, there are several, the work by Ann Meyer has observed 3 very strong resonances in this very low energy region. And we have included the lowest resonance from this work that have not been seen in the oxygen 16P alpha data. And they have also observed 2 other very strong resonances about 1.2 and 1.6 MeV in center of mass energies. And these 2 resonances have not been observed in the oxygen 16 data as well. And this part of the energy scale affects the lowest temperatures for the reaction rate. So in order to have a continuous astrophysical S-factor, as you can see, roughly at about 2.3 MeV in center of mass, the astrophysical S-factor drops down significantly, because it only has the contribution from the oxygen 16 ground state. So in order to have a continuous astrophysical S-factor, we sort of interpolated, we added some interpolated data in order to make it more continuous. And we added 3 different data points, and these 3 are shown in the magenta colored diamonds in the middle. And the cross-section uncertainties were roughly was about 20% that we added for this. And the energy uncertainty is stemming from the similar energy uncertainties for the music measurement that we provided. So using these uncertainties and the low energy measurements coming from the previous inverse and alpha transfer measurements and the total alpha P reaction measurement that we did for the high energies, we were able to calculate a reaction rate and to see its effect for the full temperature region that is associated with CoCoLab supernova. So what is shown here is this reaction rate comparison. So the plot on the left shows the reactive reaction rate in this dashed pink line. And as you can see, all the theoretical reaction rate using tallies and the reaction rate from the present work and the alpha transfer measurement are much different than the reactive reaction rate for temperatures above 4 gigakelvin or so. And the present reaction rate is different from the reaction rate by about a factor of 3 for these higher temperatures. The plot on the right here is sort of a much better representation of what's happening. And it's a plot as a ratio of the reaction rate in the reactive library. And as you can see, again, for temperatures higher than about 4 gigakelvin, the reaction rate from our measurement, from our data, actually is about a factor of 3 higher. And this has a much smaller uncertainty than the previous measurement using the alpha transfer reaction from the lithium-7T measurement. And this is mainly at the higher temperatures. This is mainly due to the inclusion of the higher contribution coming from the higher excited states of oxygen-16. So that is the most significant results of this entire measurement. So I would like to summarize by saying that the first direct measurement of the nitrogen-13 alpha P reaction was performed at using MUSIC at Argonne National Laboratory. And then we calculated the total reaction cross sections for a center of mass energy range of about 3.2 to 6 MeV. And for the higher center of mass energies, the excited states of oxygen-16 contribute to the total reaction cross-section. And this affects the reaction rate for higher temperatures relevant for CocoLab supernova. So I would like to thank all of the contributors for this measurement, everyone from Argonne, as well as Peter Moore for the theoretical calculations. And thank you everyone for listening.
I think applause in the virtual space is hard to give, but probably everybody feels by like clapping right now. I have one question out in the chat by Tenglek Ku, who's asking, what is the relevant temperature range for supernovae in this reaction?
For the temperature range for CocoLab supernova that has been shown in one of the most recent sensitivity studies is roughly from about 2 to 6 gigakelvin temperatures. For the explanation of the abundances in, say, the silicon carbide grains, it's temperatures that are lower than 1 gigakelvin, for example.
Okay, thank you. Are there more questions? You could type it in the chat, or you can unmute yourself. I think at the moment we're not talking over each other.
I have a question. I raise a hand. Is it seen?
I see a raised hand right now, yes. Please go ahead. Oh, I have a couple raised hands now. I have a bigger chat window on my other screen. Okay. Vlad, please go ahead.
So I believe these measurements are very important. Besides the data which they provided, it's also important that method is developed, and it's very important. So, but I would like to ask about the following. Carbon-13 alpha N reaction, mirror reaction. I believe it was well investigated. But can we get information about decay to the excited states, population of the excited states of oxygen from this data? I understand that you should take into account Coulomb barrier, but the states, they can be identified because it's high excitation energy.
Not specifically from this measurement, but we do have reasons to believe that using similar from other reactions that have been measured with MUSIC, that you can sort of identify the different reaction channels in the final states.
No, I mean independent measurements of reaction when you use interaction between alpha and carbon-13 to get oxygen-17.
Mm-hmm.
And then decay of oxygen-17 to the excited states of oxygen. So you know what kind of states can decay to the excited states, not to the ground state.
Ah, I see what you're saying. It hasn't been done with this technique so far, as far as I know, but I think it's definitely a possibility, maybe.
I just think that probably it's known, because it's, as I think, that it is very well studied reaction, because it's very important as a source of neutrons in stars.
Sure.
And it's easy to study because carbon-13 is stable.
There are different alpha N measurements that have also been done with music, but I'm not sure if the different reaction channels have been able to be identified separately, because this works very easily with the full. You can easily calculate like the full reaction cross section, but when you want to try to separate out the different sort of reaction channels for oxygen 16, it could be somewhat easier, because the difference between the ground state and the first excited state is there's a big energy gap of 6 MeV. So maybe the analysis can be improved in the future to measure the different reaction channels. And if so there are plans to turn music into sort of like a TPC structure, where where there'll be a higher sensitivity to the proton that is produced in this reaction. So if you can also measure the energy loss of the proton, that can also give you a little bit more information about the different reaction channels, and that can separate out the contributions from all of these channels as well.
Thank you.
Okay. I think, Grisha, you have your hand raised. Would you like to ask a question?
Yes, actually, I was going to ask about plans on separating the different channels, and you just you just answered that question. But I also was going to suggest maybe thinking about adding gamma ray detectors. I know the efficiency, of course, is an issue, but if you can measure gamma rays in coincidence, that would help you very much in separating different decay channels, right?
Definitely.
But you answered that question already. Thank you.
Okay, Phil Adsley has his hand raised. Please ask.
Hello. Can you hear me?
Yes.
Perfect. I really enjoyed your talk. I have two questions. One of them is, you were comparing to Anne's paper, and I was wondering what happens if you compare to Anne's paper without changing the low-lying resonances, of just kind of leaving everything there the same. Because there's lots of things moving, like you've got your measurement and then you're saying, oh, there's the P alpha, which is also different. And I was wondering what happens if you change one thing at a time. Do you? Yes,
so I did actually do that in this analysis. So this very strong resonance at the lowest energies that's shown in this plot here. This resonance mainly affects so all the energies roughly up until about 1.3 or 4 MeV, they affect the lowest temperatures of the reaction rate. So temperatures below 2 gigakelvin. So if you take out this very strong resonance from the Meyer paper, that affects this lower temperature. So as you can see, when I sort of plot the reaction rate as a function, as a ratio to the reactive rate, you see that the reaction rate sort of like goes up towards around like 1 gigakelvin, and that's one of the reasons for that is that strong resonance from the Meyer paper.
Okay. And the second question is there any experimental information on those branching ratios? Because you said that Peter Moore had done some TALIS calculations. And what we found is that TALIS was really bad at branching ratios. Like it sucked, frankly. It was like a factor 2 out or something, 2 or 3 for the ground state branching.
Mhm.
And I was wondering if there was a way of, like, maybe from what Vlad was saying with the alpha n, if there was a way of kind of some experimental data that could be used to constrain it, or from your experiment.
Not from this measurement as of now, but I think in the future with upgrades to the music detector, that would definitely be a possibility.
Okay, cool. Thank you very much. I should be quiet now.
Okay, there was one comment in the chat by Jeff Blackmon. I'll read it to you. What limited the 30 nitrogen beam intensity, and can you do better now?
That is actually a question that I'm not really familiar on how to answer, because this measurement was something that was done before I joined Argonne. So I don't really know what were the limiting factors for the nitrogen 13 intensity. I'm sorry. I can find it and let you know.
Maybe somebody else wants to comment?
I can comment if it's okay.
Please, go ahead.
Yeah, we don't know what was limiting the reaction. I mean, the rates. That's just what we got. Probably the transmission was not very good. We saw that from the production to music, we were losing a lot somewhere in the line. But that was before Razor, and with Razor, we hope that we can do better, but we haven't tried again, and we don't know by how much better we can do.
So maybe I wanted to ask in that direction as well. What is limiting your sensitivity right now with this setup? I mean, it's obvious that it has really strength and is getting you very reliable data. What is limiting the sensitivity ultimately? I mean,
One of the
one factor, obviously, but
sure. Well, one of the things is that when it comes to, say, the total reaction cross section, one thing could be the segmentation of the anode of music. So the uncertainty for each of the energy in a set of mass energy data points that we obtain is limited by the energy loss of the beam within a certain width of the strip. So maybe this is one that can be worked on in the future as well. Mm-hmm. But also the beam, the rates that music can handle also is a limiting factor to go to much lower reaction cross sections. So if we can find out, come up with a way for music to handle much higher beam rates, then we can go to very low reaction cross sections, and that would be great for astrophysical measurements.
Okay. Omaldo, I see your hand raised, please.
Yes, so just Heshani, I enjoyed your talk. Just to this last point, there's a recent NIM paper by Johnstone et al., which describes exactly how you are able to localize the position of the reaction to sub-anode level. So you might want to familiarize yourself with that if you're not aware of it.
I am not. Thank you very much for bringing it to my attention.
Any more questions? Any more comments, please? Well, it seems to be like everybody's satisfied and impressed, and you wrestled them into submission, Heshani. I would just like to thank you again for this presentation. It was a pleasant afternoon for us, and maybe leave it at that and send everybody home now. Thank you very much.
Thank you for attending the talk.